Oh, wow.
Hello, hello.
Hello. Good morning, everybody. Welcome. Hopefully everybody's having a great week here at reInvent. And thank you for joining us for this session today, where we're going to dive into how you can actually migrate and modernize your web workloads with Amazon CloudFront. I'm Tino Tran. I'm the worldwide tech leader for Edge Services. And today I actually have the pleasure by being joined on stage by one of our customers who's actually a significant user of the service, Ali.
Yeah, thank you, Tino. This is Ali, and I manage global traffic distribution for Booking.com. We are going to take you into our incredible journey of migration and modernization of our Edge services. And yeah, I hope there's something for everyone today.
Yeah, we're actually really excited to have Ali on stage with us because there was a lot of learnings and insights from their modernization journey that we wanted to be able to share publicly because we think it's really relatable for a lot of our customers, right? So we're going to share a lot of those insights. We're also going to talk about some techniques we've learned in working with other customers as well. So just keep in mind, this is a 300 level session. We do expect that you have some familiarity with content delivery networks and basic web primitives like HTTP and so forth. However, if you don't, we'll do our best to bring you along. Just remember that as you're filling out the session surveys. All right, let's get started. Okay, so a lot of times when we work with customers going through cloud migrations, one of the first questions that we see asked is, how do we move the workload? Do we modernize, then migrate? Do we migrate first, lift and shift, et cetera, et cetera? Everybody wants to modernize. It's still a buzzword, just like AI is today, so it's very important. But the truth is, when you're moving to the cloud, you're already going through some degree of modernization. You're giving yourself access to more modern infrastructure, more capabilities so that you can operate more effectively, and more features and capabilities so you can continue to grow your service out, right? But how you move really depends on your immediate business need at that time. A lot of times when we see customers go through data center exits, they want to move as quickly as possible. So lift and shift makes sense, and that's actually something we prescribe. However, something we also prescribe is looking for opportunities to leverage cloud-managed or cloud-native services in parallel so that they can build experience and really see the return on investment and that value of using cloud-native services and build experience using and operating those services. So in today's talk, we're actually going to focus specifically on that, how you can use CloudFront as a cloud-native service to migrate and modernize your workloads. Okay. So CloudFront, it's our content delivery network service, and it's actually one of our oldest services. We've continually grown it over the year, and the primary focus behind the service is to use it to help you accelerate web workloads and also protect them from threats of the internet. Now, as I said, we've grown the network over the years, and we continually invest in improving our infrastructure and scaling out, as well as modernizing that infrastructure stack. So we have a tiered architecture. We have edge locations around the world called our edge POPs, points of presences. These edge POPs are deployed in major cities around the world. Usually there's one or more of them in those areas, depending on the capacity that's needed. And they're deployed close to transit centers and internet exchanges so that we can get closer to end users, right? Behind these edge POPs, we have the regional edge cache. Regional edge caches are our mid-tier cache. They're basically super POPs. We deploy them directly within AWS regions around the world where we have more capacity. This allows us to increase the cache width, therefore giving you better cache hit rate, as well as more offload for your origins for those cacheable workloads. Now, the benefit of being in the region for the regional edge caches is it also allows us to integrate more with capabilities across the cloud. So we can bring more capabilities to you when you're using the service. Now, something that's important to note here is between our edge locations in AWS regions around the world, we have an AWS privately managed backbone network. And this is significant. We're able to avoid routing traffic over the public internet, optimize that connection, and avoid many of the inconsistencies of routing traffic, right? And then last year we actually introduced a new type of edge location called the embedded POP. Embedded POPs are actually deployed directly within ISP networks around the world, so now we can get even closer to end users. These POPs are designed specifically for highly cacheable, spiky traffic. Think about your live video delivery workloads where a lot of traffic is coming at once, or popular software downloads, right? It allows us to kind of overcome some of the challenges of scaling at these internet exchanges and provide even better end user experiences for these workloads. So as you can see, we've continued to invest over the years on the service, and we've also added capabilities within the service as well. And to start today's conversation, we're going to start by sharing Booking's use case to show you how they've been able to take advantage of some of these capabilities.
Yeah, thank you, Tino. Over the years, Booking have grown from a small Dutch startup into one of the biggest e-commerce in the world right now. We are making it easier for everyone to experience the world. No matter who you are, where you want to go, we will make it happen. That's why we invest in technology. And we work tirelessly to remove every aspect of friction from travel. Let's talk some numbers. Since 2010, we welcome more than 4.5 billion guest arrivals over many of our incredible destinations and types of stay. And it's not only hotels. We offer homes, apartments, stays, heck, even bungalows, igloos, and tree houses. Over 175 different locations around the globe. And on top of that, we offer ride-sharing, rental cars, taxis, attractions, experiences, even flights between all the major airports in the world. And you can imagine how big is that scale. All this together is generating tens of petabytes that have to run through our edge and hit our different data centers and AWS regions. Our ecosystem is quite diverse. After all, we have around 3 decades of engineering innovation under our wing. Since 1996, our talented engineers have been building different types of infrastructure and architecture, from different types of monoliths to microservices and containerized application. We run our own data centers, we have our own private cloud, and we also adopted public cloud for quite a lot of our workloads. But I'm here today to focus on one aspect of our infrastructure, which is our traffic engineering. Going back around 10 years back, we used to buy hardware appliances to run as our own L7 load balancers. Those worked great, but it was a manual configuration and install. Scaling them was hard because they only scale vertically. We always have to provision double the capacity to have a passive active backups. They worked okay, but as booking was growing fast, we needed more. So we decided to build our own load balancers using a combination of the open source HA proxy, multi-path equal cost routing, and Anycast. We built a product we call distributed load balancer, deploying it in our data centers and configuring it with a central place to configure all our load balancers. And that worked really, really well for us for a very, very long time. But booking kept growing, actually kept growing globally and exponentially, that just having our own data center load balancer was not enough. So we started building something we called mini-POP, just minimal points of presence. We deploy somewhere around the world, and then we connect to our main data center through the leased lines and dedicated lines. And those served as our own in-house content delivery network, or reverse proxy globally. That really helped us looking around the globe where we have enough cluster of customers. So we build the POP. Now we make sure we have the best connection. But booking kept even growing. And those many POPs were not easy to manage. We have to handle contractors around the globe, run data center space, and have to figure out a way to make the connections reliable and add redundancies. It was a lot of work. The operational burden started hurting us. And the return of investment was very quickly just not enough for us. So we decided to take a step back and review actually what do we need. This came in a time where we observed a growth in the adoption of public cloud. So we set it as one of our requirements. We need a solution that will help us accelerate our cloud operations. We needed something that can actually relieve us from that operational burden. We needed something with a measurable, easy to detect performance improvement. We needed something that adheres to our very high standards of compliance and security. And finally, we needed something with a very fast, very reliable backbone around the globe. And this is where...
So, as we were working with Ali and his team, it's very quick that we realized that CloudFront was a perfect fit, right? They had data centers where they're hosting their applications around the world. They're also deploying their applications in the AWS cloud now. And they're deploying the mini-POPs to execute some middleware logic and route traffic across these origin servers that they had. So CloudFront actually does a lot of this right out of the box. You can actually use CloudFront as a reverse proxy, meaning no caching, right? And out of the gate, you get a lot of benefits in terms of performance, reliability, and security just by doing that. That's something a lot of customers don't realize. On top of this, we're origin agnostic. You can route traffic to any origin, whether it's in AWS or not. And we provide edge compute capabilities in the form of Lambda to edge and CloudFront functions so that you can execute logic in the edge closer to your end users. All of these worked out greatly for their use case because, if you look at the mini-POPs, we're kind of doing a lot of this for them out of the gate.
So actually, that was very surprising to part of my team. We've been using CloudFront for years, at least 10 years by that time. But we're used to it as our content delivery network where we cache our static assets, and it works perfect for that. But using it for our dynamic content, that was unique. But thinking about it, with 700 POPs around the globe, utilizing all the features they already built and their very strong backbone, makes sense for us. So we decided to give it a go. But before we can put any production workloads on CloudFront, we decided that there is basic foundation, scaffolding if you want, a foundational requirement that we need to build on the cloud before we can actually move on. Starting by building observability and troubleshooting tools, then building the security and compliance to secure the communication between the customers and CloudFront, and then from CloudFront to our origins. After that, we needed a way to measure that performance and improve it with data. It does not cut it at booking just to decide to do something without data to prove it. And finally, we needed to put our routing configuration on the cloud as well. Starting with observability.
Yeah, so when it comes to serving web traffic over the public internet, we know that our customers need visibility in a number of forms, right? First, they need to be able to see traffic and analyze it over a large period of time. They want to know where the users are coming from, what type of requests they're getting, what type of responses we're returning, even country information. And we make this available through standard logging or access logging, and these logs are deployed directly to S3. But actually, as a matter of a couple of weeks ago, we introduced a capability to deliver them also to Amazon Data Firehose and CloudWatch logs. So you have more options now on where you want to analyze your logs from. There's also a need to see this data in real time. So think about when you're delivering a live event or making a major change or deployment. In the context of migration, it makes a lot of sense to kind of keep an eye on that change, right? We offer real-time logs. So real-time logs offer all the same log fields as standard logs deployed to Amazon Data Firehose, where you can kind of deliver that to any log analytics engine of your choice. And something that's important and worth noting is when you use real-time logs, you can actually get additional fields such as origin latency metrics like first byte and last byte latency, as well as information about where your clients are coming from in the form of an ASN number. So I talked about edge functions a little bit earlier when I was introducing the service. When you're writing function code that's deploying anywhere, you need to be able to troubleshoot it. And sometimes you might use your logs to do some other analysis on like custom data that you might be logging. So we provide CloudFront function logging and Lambda edge logging through CloudWatch logs. The logs are delivered there, and you can run queries and insights directly within that service. Something that's very important that's worth noting, though, is CloudFront functions execute at our edge POPs. Lambda edge functions execute within Lambda at the regions that we replicate them to around the world. So the logs are delivered into different places. Function logs are delivered to USD East 1, where our control plane is, whereas Lambda edge logs are delivered to the regions where the function is actually invoked. Now, on top of this, we also realize that metricing is important. You want to be able to set up dashboards and alarming. We provide this in a number of different ways. Through CloudWatch, our monitoring service, you can create custom dashboards and alarms. And then we also have standard dashboards that are available in the CloudFront console as well.
Yeah, with that, we were actually armed with everything we need to build our own observability. So in the beginning, we just took standard logs, dumped it into an S3 bucket, and we simply used Athena to see what's happening on the edge. But that was very slow for us. So we started taking all the standard logs using the OpenSearch ingestion service and putting it in OpenSearch, where the logs are now being indexed, and you can easily query them very quickly. But because the massive scale of that, we decided only to put the error logs and not care a lot about access logs at that stage. And then we looked at the real-time logs. In the beginning, we did not have the newest feature of dumping the real-time logs directly into Kinesis. So we wrote our own Lambda to sample the real-time logs and get them through Kinesis, Firehose, and Stream into the OpenSearch as well. But as the services were provided from AWS very recently, we just sample the real-time logs. We take very small percentage just to keep the cost sane. And we put it in OpenSearch as well to generate our SLIs and SLOs. And we look at different rates like error rates and all the different metrics we care about. And for our edge compute, we simply just use CloudWatch. It was good enough for us. Finally, we used the Amazon CloudWatch Internet Monitor. It's a service from CloudWatch that gives you observability on the last mile communication between the different customers around the globe. This, in combination with the ASN data that is available in the real-time logs, allowed us to really look at every cluster of clients around the globe and how speedy is their connection. I have very, very vivid memory working with the AWS networking team, our networking team, and some random ISP in some country in the world, trying to optimize that last mile communication as we see. And in the end, we built our key metrics to adhere to our observability and resilience standards. So we looked at the error rates, detailed error. That's a metric from CloudFront that gives you very clear observability to what kind of error happening between the TCP connection between CloudFront and the origin, the TLS termination. And then we collected more metrics about Lambda, our cache hit ratio, and the latency across the board. And with that, we finished our first pillar of foundation to start using CloudFront. The second one is securing the communication. For that, we actually found a very, very easy solution. In a CloudFront log, you can use the QR code if you want to look more in details. There is a native feature in CloudFront where you can inject a header, reading a secret value from the AWS Secret Manager. And if you are within the AWS ecosystem, like an API gateway or an ALB, you can protect it by WAF, and WAF will make sure that this secret with the right value is there. And we simply piggybacked on that solution. In our distributed load balancers, in our data centers, we directly took the secret from the secret manager. And on DLB, we built 2 layers of security. The first one is only whitelisting the IP addresses of CloudFront. And the second one is making sure that secret exists. And with that, we secured the communication between CloudFront and our data centers. And to secure the communication between the end customers and CloudFront, we simply dumped all our SSL certificates into ACM. We used them to add aliases to our CloudFront distributions, and that was good enough, in addition to the standard use of WAF and Shield.
Awesome. So, security is important here at AWS, and we're constantly working hard to make it easier for customers, because the harder it is to implement, and the less security you might have, right? So when you're using cloud native origins, so first and foremost, Ali shared how you can use the shared secret header with IP whitelisting to protect that connection between CloudFront and the origin. And that works for all different types of origins. If you're using cloud native origins like S3, Elemental Media Services, Lambda function URLs, we actually have a feature called OAC, Origin Access Control, built into it, where you actually configure an IAM policy that specifies exactly the CloudFront distribution that has access to that resource. From there, when a request hits CloudFront, we inject an authorization header using SIG-v4 protocol. It's an open source protocol that we publish. And the benefit of this is we're managing that signing, right? We're using ephemeral tokens, which makes it more secure, reducing blast radius and entry points for threats. Something that's worth noting is, it's very important, when you do this, CloudFront injects the authorization header. If your clients are sending an authorization header, we will override that. So something to think about when you're designing your applications. There are use cases where you want the client to inject the authorization header and keep that, and you can configure CloudFront to not send that forward. But just keep in mind, you'll have to update your IAM policies accordingly to make sure that that validation matches up. Now, something very exciting for us is just a couple weeks ago, we launched a feature called VPC Origins. So now, in addition to cloud native origins, if you have origins in EC2, we can actually establish a secure tunnel between CloudFront and that origin that's in a private subnet. So you no longer have to expose that to the public internet and create routes to your internet gateway, right? We use VPC to VPC natting to establish the secure tunnel. It's great because it allows you to reduce your surface area of attack, making CloudFront the true front door endpoint for any public-facing web application, which we actually recommend. And you can save on IPv4 costs. Now, earlier I mentioned that just by using CloudFront as an inline proxy, you get a lot of benefits out of the gate, one of those benefits being security. This is a big deal, right? When you use CloudFront, a packet enters our network at an edge location, and we have a lot of protections built in right at that front door. We're checking the packets for correctness, we're looking at DDoS threats and scrubbing that traffic, and we also have the ability to deploy a known offenders list based off of threat intelligence data that we're looking at across our AWS network. So this all happens at the front door before it even gets any closer to your application and before we even terminate the request. When we terminate the request at CloudFront, we make it easy to do. So Ali mentioned that we are integrated with a service called Amazon Certificate Manager. It is a certificate authority. You can actually get free certificates from ACM when you use CloudFront and deploy them right there, or you could bring your own. But we want to make that readily available and easy to use for our customers. Now, on top of this, we're always monitoring the service in detail. We're inspecting web traffic, common patterns for establishing a connection, common flows, and because of this, we're actually able to identify issues before they happen, looking for inefficiencies across how clients are connecting to us, right? A good example of this is Last year, we had a big attack called the HTTP2 reset attack, where there was, I think it peaked at over 155 million requests per second. Because customers were using CloudFront, they were largely unimpacted because many months before, our engineers were looking at how the connections were being established. They saw a vulnerability there, and they were actually able to put in guardrails before the attack ever became a real attack. Now, on top of this, we're also integrated with a service called AWS WAF. WAF is Web Application Firewall, Layer 7 protection. You can configure rules, custom, manage rules. Third-party rules are also available there. Through CloudFront, we offer one-click integration where we can deploy a default rule set for you. But all of this is available to you right at the edge, and truly, using CloudFront for any public-facing HTTP traffic is a best practice at AWS.
Yeah, and with that, we covered the two main pillars of our foundation, which is observability and security. Now we need a way to measure the difference between using CloudFront as our edge and our legacy solution of Minipops. To understand that more, let's look at a typical journey of a web request coming to your backend. Usually, we start with a DNS query, then to a TCP handshake, into TLS termination. And then the request is going through your edge all the way to your backend. And then the backend will take its time calculating what needs to be sent back. And then once the browser receives the first byte back from your backend, this is what we call time to first byte. And this is our first metric of performance. Once the browser have enough data, all the HTML, and have enough to build a DOM object, that's what we call the DOM loaded time. And once the browser have loaded all the static assets, JavaScript, CSS, the images, etc., that's what we call the window loaded time. It was very easy for us to just look at the TCP termination or TLS termination, which we saw drastic improvement on that. With the 700 Minipops around the globe, it was big. But with our customer centricity, we decided to look at only the performance metrics that really reflects into convergence, which in our case is the DOM loaded and the window loaded time. At Booking, we pride ourselves of having a big culture of experimentation. Everything has to be data-driven. And we have a very comprehensive and big experimentation system running inside the company, where almost at any point you touch Booking.com, there will be 1,000 experiments running. Sometimes it could be sending you between two different architectures, two different backend services. Sometimes it could be just a color of a button, red or black, and see how that affects the customers. And this experimentation system runs in a very early stage of our backend processing time. So using that experimentation system to decide between our edges was not an easy task. It is not something you can decide with a cookie or a user ID. So we needed to get creative to actually be data-driven. So teaming up with our data science team, we designed our own experiment, taking one service from Booking.com and shifting 100% of the traffic of that service every 4 hours window between variant A, using our Minipops, into variant B, using CloudFront as our edge. And to make sure this data is consistent, we shift that 4-hour window by 1 every day, so the same user is not hitting the same variant of every hour of every day. And to make sure this data is statistically significant, we kept this experiment running for 2 full weeks, actually 3 weeks. But we took 2 weeks to measure the performance. And to our surprise, we saw improvement across the board in every region in the world. That was very surprising to me, because even in the regions where we have our own data centers, it was faster to go through CloudFront to our data center than going directly to them, which actually stumped me personally. How come adding another hub into the request is actually improving performance? Actually, overall, we saw the load time improving by at least 10% in remote regions, and sometimes up to 30% in some remote countries, which is definitely can translate into convergence. To you, Tino, too.
Yeah. So, actually, it's interesting, right? A lot of times when we introduce a service as a reverse proxy for dynamic content acceleration, the first question that pops up is, how does this work? We're adding this extra hop on the request response path. That physically doesn't make sense, and it's not intuitive. But when you really look into how this works, when a user makes a call to an application, the first thing that has to happen is it has to establish a connection. Now, the further the user is from where that application is hosted, there's a latency penalty, right? They have to traverse over a long distance, and we're really dealing with the speed of light. When you use CloudFront, the users now terminate the connection much quicker at the nearby edge location. And then on the backhaul between the edge location and the service, we're maintaining persistent connections, which allows us to do a number of optimizations to provide better throughput and performance for our customers. Now, it gets even better. If you're using AWS, you have your origins in AWS, we're able to use our backbone network, which allows us to avoid many of the inconsistencies of routing traffic over the public internet. When you route traffic over the public internet, the capacity and the bandwidth varies depending on how busy the internet is at that point in time in the day. When you use CloudFront, we're monitoring this, and we're managing all the routing to make sure our traffic between our regions and our data centers in the form of POPs are readily available for our customers. Now, to take a deeper look into some of these optimizations, the first thing that happens is a connection, right? And over the years, the protocols have advanced. There's HTTP 1, 2, and then recently HTTP 3 over UDP with quick protocol. But like that connection has to establish first. And one of the things we learned in talking with customers is it's really hard for them to stay up to date with the latest standards and leverage all of the capabilities built into the protocols. So we'll do that for you. It's available in console. You can actually just configure and use it. We also understand that there's bidirectional use cases, and we make those protocols readily available through WebSocket protocol. And actually recently, just a couple weeks ago, we launched support for gRPC. gRPC is a bidirectional protocol. It's more compressed. It's done over HTTP 2, and you can actually establish a gRPC connection now from your clients all the way to the origin server. On the backhaul, we do a number of things. We talk about optimizing the TCP congestion window, right? So TCP has this thing built into it called TCP slow start, and it's really intended to make sure that you don't flood the network and measure it gradually as you use that connection. So it'll linearly scale the congestion window over time. When you use CloudFront, we have some optimizations that we do. We're looking at, we take advantage of features like TCP fast open, SSL session resumption. We're also able to, and when it's in an AWS origin, we're also able to scale that up much faster and increase the congestion control window. Now lastly, something that's important that's worth noting is, with the exception of gRPC, that connection between your origin servers and our CloudFront edge locations is done over HTTP 1. We find that it allows us to give the most performant experience because we're able to do all these TCP tricks, right, and really collapse these requests.
I actually would like to reiterate in this point because this was a major factor of our adoption to CloudFront. Just think about it for a second. 1,000 customers in one edge location. They're all starting a new connection with the CloudFront. Then CloudFront is establishing one connection from that edge location with our origin and sending all of them together. We saved a huge amount of time of all that TCP and TLS termination back and forth. And that was a major factor of why we saw that big improvement of the communication. So we established our observability, we established security, and we did the experiment. We proved to everyone that CloudFront is good for us. Finally, we needed to tackle a problem, which is setting up multiple origins behind the CloudFront. To understand this problem, let's go back to our mini-POP solution. Our customers we were using a combination of GeoDNS and weighted policy routing policies to send our customers to the nearest POP and then route the traffic and balance the traffic equally between multiple POPs in the same area or multiple data centers. But as we went to CloudFront, it was a little bit different. We decided to use CloudFront everywhere, even in the areas where we have our data center, to have consistency of experience for the customers. But now we don't use GeoDNS to use the nearest POP. Actually, CloudFront does this for us. But behind the CloudFront, in some cases, some of our services, they run in multiple origins in the same time. Those origins could be in the same time, an AWS region and a data center. And we usually would like to distribute that traffic between those origins more or less equally. That helps us manage our capacity better and also manage the cost on AWS better. But unfortunately, CloudFront does not come out of the box with a native feature to load balance the traffic between multiple origins. So we looked at multiple ways we can actually achieve that, like using Lambda on the edge. And we ended up just using Route 53. It was quite straightforward, actually. Just behind CloudFront, we set up a domain, like, for example, origin.example.com, using Route 53 weighted routing policy, where we add all our origins as an entry into that routing policy with equal weights, expecting the traffic to be equally distributed between those multiple origins. And the added value to that, it is very easy with Route 53 to add health checks. So if we lose one of our origins, the traffic will be automatically redistributed between the others. So looks good, looks great. There is nothing to it there. We expected to just continue to see those smooth lines we used to see between the multiple data centers. But in reality, after we adopted CloudFront, this happened. We started seeing spiky traffic, erratic behavior of requests, jumping up and down. Sometimes it could be very big, up to 40%, which resulted in us having to deal with capacity problems. And it was very hard to also manage resources in AWS. The traffic is jumping between 10% to 30% within a few minutes, actually. To take a deeper look what actually happened here, let's look at the individual customer, what's happening with them. Usually, the individual customer is sending his own DNS resolution and hitting Route 53 as an individual customer and getting an answer after the coin toss to hit one of the origins. Therefore, since every query to Route 53 represents one customer, we see equal distribution of the customers between the data centers. But as we adopted CloudFront, now the customer is always hitting the nearest edge location, and that edge location can be handling many other customers at the same time. And then that edge location from CloudFront will send one DNS query to Route 53, but it's not representing one customer anymore. It's representing a cluster of customers on that edge location. And here's the critical point. The edge location will actually cache that DNS resolution. Therefore, for that TTL of that cache, all the customers will be hitting one entry point behind the origin. So imagine if we have, 10 edge location. One of them is 1 million customer. The other have each 1,000 customer. That 1 million customer will be shifting altogether between origin A to origin B to origin C, therefore seeing that drastic change. But on the added point of that, the more customers are using the same IP, the more connection reusability will be there. Therefore, just after adopting CloudFront, we saw the doubling of the ratio of connections to requests. And after we kept fine-tuning our connection timeouts, our TTLs of DNS, we saw up to 6x in connection reusability, which for us is critical because the more a connection is reused, the more we are saving time on TCP and TLS termination. And with that, we established all the foundation we needed, and it's go time. It is time to start migrating all our workloads to using CloudFront. We expected after all that for that to be straightforward, but it was not. So let's talk how we migrated first. Usually, when you want to migrate something in a typical change management fashion, you always need to start small and grow gradual. And Route 53 was an excellent tool for that. We have many, many routing policies we can use with Route 53 that allow us to actually cluster our customers in different ways, in regions, in IP addresses, or even just percentages. Before we start anything, if you're doing a migration with DNS, you have to reduce that TTL into as minimal as possible, because you will be changing a lot, so you need that DNS changes to be propagating very quickly. And our method of choice to gradually increase the use of CloudFront was, again, the weighted round robin policy. Using this excellent trend of 1% canary, just sending 1% of your traffic through the new method, will expose all sorts of issues. We did our homework, we promise. We looked at all the standards and limitation of CloudFront, and we tried to anticipate every possible scenario where something can go wrong. But you will never get it all. You have to send a little bit of your production so you can actually see what's happening. And that's exactly what happened with us. We went the 1%, we learned from that. Sometimes we had to revert to look at what happened and the problems. Just very recently, we've been working with that. And then we increased from 1 to 15 to 50%. Eventually, once we feel confident enough, we go all in. As we do that, we learned a lot about how CloudFront work, about how the edge locations work, about how actually the global networking and how it is interacting with us. Some of the very interesting facts that actually we stumbled on the way. CloudFront adheres to a very high standards, or adhering to the standards of RFC. For example, RFC says that the maximum URL length shouldn't be more than 8 kilobytes or 8,000 characters. In our case, we saw some bad actors having URLs with the GET parameters more than 30,000 characters. So we had to run after those actors in the company and ask them, what the hell are you doing there? Why you have a URL of 30,000 characters? There must be something wrong there. Are you sure you need to use a GET, not a POST? Are you sure your service is doing it right? we found actually some recursion errors where the same parameter is being added over and over and over. So that exposed some opportunities actually for us to modernize, and we had to do that before we can actually go full on with CloudFront. The second one, out of the box, CloudFront comes with a 30-second connection timeout. In our case, we also have bad actors. Some of the long pooling use cases where they wait up to 5 minutes for a request to terminate. So we had to revisit how we do that. We have to work very closely with solution architects, with AWS, and also with our teams to change how that services are set up. CloudFront is a multi-tenant service, so it is over for us to have our own dedicated IPs. Some of our partners use the old method of securing traffic just through IP whitelisting. So we needed to work with our partners, figure out new and more modern ways to secure the communication.
Yeah, awesome. I mean, like these learnings that Ali had just shared, right? Like they're common across lots of customers, especially when you're operating a custom environment that you're self-managing. You can get away with a lot of, customizations that may not be up to date with the latest web specs. So worth calling out here is when you're moving to a service like CloudFront, that's a shared service, it's a multi-tenant environment that's hosting web traffic of all sorts of different workloads at huge scale, there's going to be learnings that you're going to have to adapt to. So with that said, CloudFront puts these guardrails in place for a reason, right? We adhere to the HTTP standards, but we're also monitoring traffic to see how clients and customers are consistently using the service. And we put these guardrails in place so that we don't have misuse that could affect all of our customers. In addition to this, we put guardrails in place to protect customers from themselves, right? So a good example of this is persistent connections. So Ali mentioned that the connection timeout, they could only increase it to a certain amount, and it wasn't working in their original setup. Well, to help you better understand this, let's take a look at how we build these CloudFront POPs. So CloudFront is built on a tiered architecture, and this is highly abstracted. There's different layers with different responsibilities. And within one server, we have multiple tiers. Across an edge location, we have multiple servers, one to many, in some places a lot more than others, right? When a web request hits our edge location, we do some ECMP routing. We route that traffic to a server, and then we do some consistent hashing to make sure that we use the best of that resource and really kind of provide as much reuse as possible, right? We respect DNS, and we cache based on the IP address, so that's how we manage our cache pool. Now, depending on how the request comes in and how you configure your distribution, that flow might change. In some cases, it might skip a certain layer if it's not cacheable content. In other cases, it might go directly to the regional edge cache where we're invoking cloud native capabilities. It just varies. But the thing I want to kind of take away from this slide is we can establish connections basically at any point across our fleet of servers. And earlier we showed a slide where we're in over 50 countries, over 100 cities worldwide, in each one of those cities, more than one edge location. So if all of these servers end up opening a connection to your origin, you're going to be using those resources at the origin location and probably draining those resources that could hurt your performance, introduce latency, and so forth, right? So this is a good example of how we kind of put some of these guardrails in place. So with CloudFront, you can actually configure your keep alive timeout up to 60 seconds. However, if you have a more advanced use case, in the case of booking, we will work with you. Just open a support ticket, and CloudFront Engineering will hop on, understand your workload, and we'll adjust accordingly to the best ability that we can. Another learning that comes from these migrations is not just for our customers. It's a learning for us, right? So Ali mentioned that they had a use case for static IP addresses. We also hear this across a lot of different customers. And in the past, we weren't able to do this because a lot of the way that we do routing is dictated by how we assign IPs across our edge locations. When a request lands on CloudFront, we do a DNS-based routing. So we do a lookup. We take a bunch of parameters into consideration beyond how close the POP is to that end user, because we want to make sure there's capacity, the POPs are healthy, and between all of these attributes that we're constantly measuring and monitoring, we can serve the best performance accordingly. And through that, it'll return an IP address, and that IP address will take you to an edge location. These IP addresses might move around, but that's how we kind of route and determine where the traffic should go. So just last month, again, we launched a new feature called Anycast Static IP Addresses. So today, you can actually get your own static IP addresses from CloudFront. and use that for use cases like zero rating, or for some customers, they want to make sure that they only whitelist egress from their private networks for their users to certain IP ranges, right? With Anycast IP addresses, we actually use Anycast protocol to route the traffic to the server. So we do this over BGP protocol. And then from there, we have route tables that determine if we should forward that request along using a GRE tunnel. Awesome. So now that we showed you what it could look like when you deploy CloudFront and use it for dynamic content acceleration, let's talk about some of the capabilities within the service that you can adapt to and really kind of do more at the edge ever than before. CloudFront offers CloudFront Edge functions. These edge functions are offered in a couple different ways. We have Lambda Edge, which is actually Lambda, except unlike Lambda, when you deploy a Lambda Edge function, we replicate it to the regions around the world where we have a regional edge cache, and you can invoke the functions from CloudFront through there. The other capability that we have is CloudFront Functions. CloudFront Functions is for, these functions execute directly within our edge locations, and they're really designed for high volume, low latency executions. They're very latency sensitive. They execute within under a millisecond, actually. Lambda Edge, you can run the functions a little bit longer. You can make network calls. You can do more manipulations, integrate libraries, and so forth, right? But on the left here, you can see that like there's a number of use cases that are available, and these are use cases that we've learned from customers looking creatively on how they can do more at the edge than before. But ultimately, what we actually see is, the real value that we see from a lot of customers is it helps them centralize that application logic for core common logic to their SRE teams in this case, or systems teams, so that their application teams don't have to inconsistently deploy and make updates for common logic like redirects or normalization or cores and so forth. And it actually gives them an opportunity to manage the capacity much better, because now you're going serverless and you're doing this through the edge locations through a cloud native service. Okay, so over the years, we've seen customers move to more modern architectures. It started by microservices, and now for the front ends, we're seeing customers adopt micro front end architecture. This allows their teams to own independent domains within the web application, deliver independently. It provides them with more agility and so forth, right? And when you're migrating or making changes to any web application, Ali mentioned before, you want to go slow. You want to start small, and you want to move gradually. So you have to be able to do this across the assets or the domains that are owned by these teams. Typically, this is done using a subdomain to assign ownership to the individual components or domains that these teams own. Other times, it could be the URI or a URL path. And then for more advanced cases, we've seen customers use header values to introduce changes incrementally so that they can do their testing and test different variants and so forth, right? So to take a look at how you can actually do this with CloudFront Functions, CloudFront Functions can actually see a lot of attributes on the request. When a request hits CloudFront, in this case, we're looking at the URL, right, and the user's country. You can configure CloudFront to actually inject additional information about the request on the request response path. And then in your function, you can use CloudFront Functions with a feature that we have called Key Value Store to decide what you want to do with that. In this case, we're going to redirect that, or not necessarily redirect, we're going to rewrite the URI path to serve them tents that are designed for customers in America. If we look at the function code, when the function invokes, everything goes through this function handler. And the important thing I want to share here is how much access you have to the actual request itself. There's an event object that's passed in. It's really a JSON object. You simply parse it, and you look for the attributes that you're looking for. And from there, you write some function code to do that rewrite and make those changes accordingly. Now, in addition to being able to write the code, let's take a look at what we see most often, right? When you're making changes to a web application, it's not as straightforward as doing a DNS flip. You have users that are connecting to a service, and they have a session, and it has to be sticky. You want to make sure that they're fully tied to that connection or that experience that you're trying to do. So you need to maintain sticky traffic. And one of the ways you can do that is with CloudFront Functions. In this case, we will actually write some function code to look up a weighting policy that we might have, right? Maybe we want to send 10% of our traffic. You can change this and update it and configure it through Key Value Store to the new origin. And then based on that, assign a cookie to that session and then route the traffic accordingly. On the way back, you can set that cookie if it doesn't already exist. So we're consistently adding more capabilities within each type of runtime that we have. Origin selection with functions is a new thing that also launched just before reInvent. Okay, so that's how you can move traffic as you're making changes, whether it be a modernization or a migration for components of a web application. We're also seeing customers want to move towards more modern architectures for better availability and performance. One of the things within AWS that we've been marching towards over the past decade or so is cell-based architecture, right? When you're moving to the cloud, usually there's, in addition to performance, cost, operations, and so forth, you want better availability. And cell-based architecture is a pattern that we see a lot of customers internally and externally adopt, where you provide more redundancy through individual stacks of the software being deployed in different places. In this case, we deploy across different regions. And not only is it about redundancy of those stacks, it's being able to shard those end users so that you're not expanding your blast radius in case a bad deployment happens across any of these stacks. So typically, when you roll out a change, you may roll it out to one place. If there's an issue that got targeted by a certain set of customers, it's not affecting all of your customers, and that allows you to increase your availability posture. Now, the hardest part about this architecture is the only layer that's not redundant is the routing layer. So you can see how that could be a challenge if you wanted to implement that yourself. Now, with CloudFront and functions and all the capabilities that we just introduced, you can leverage that. Like in this example, we'll shard the traffic based on profiles of users that we have. Maybe it's a subscription plan, so that we don't impact all customers if an issue were to occur.
Yeah, and once we adopted CloudFront and we reached that 100%, and actually we put all our platforms together, multiple domains, even across the different subdomains and different URLs, we started looking into modernization opportunities. And there was quite a few, actually. I was personally very happy and surprised of how easy was it for us to adopt things like HTTP2 and HTTP3, IPv6, WebSockets, and gRPC, which was very easily implementable on top of CloudFront. We really enhanced our security posture. Our security teams don't need now to run after multiple exposed to the internet endpoints and implement different kind of WAFs and shields and bot mitigation. They can focus in one area, in one edge, just using the WAF bot, WAF fraud, and WAF Shield Advanced, which protects us from many types of volumetric attacks that can come to us. But the biggest from them all is, for the first time ever, across our very complicated ecosystem, we have one place to execute business logic that covers everything at Booking. To learn more about that, let me go back to this graph. In any multi-application tiered architecture, you usually have this common layer of common logic. This is where people usually do their security or context enrichment, or among many other things. In monolith application, we call those common middlewares. In microservices, they sometimes call them reverse proxy services, or sometimes they also call them common logic services. And as we looked at our ecosystem, that was all over the place. And inside the monolith application, we have a bunch of those. Inside our Kubernetes ecosystem, we had a bunch of those. By looking at a bunch of those and taking them all to the edge, that finally allowed our individual service owners to be free from where they are sitting right now. Basically, if you are running inside a monolith application and you really depend on that common middleware, you cannot go out. You are stuck there until this change. And just by moving some of those stuff out there, we saw an acceleration of modernization in the company. Let's look at Lambda on the edge and how it works. When the customer sends a request to CloudFront, it usually goes to an edge location. And from there, it goes into the regional edge cache. And that's what we call the viewer request. And then the request will continue to your backend. That's what we call the origin request. Once the origin sends back the results, that's what we call the origin response. And finally, the viewer response. Lambda on the edge allows you to be executed at each one of those 4 locations. But in reality, the viewer request and the viewer response were quite limited in terms of how much code you can put there and how much compute you can get executed there. So they were not the best location for us. And the origin response was already too late. We're trying to enrich the context before it reaches our origin. So that means there is only one Lambda for us, which is only the origin request. But in reality, we literally have people inside the company fighting of who should be using Lambda on the edge. We only have one Lambda to execute, so who should take it? Authentication teams, they wanted, for the first time ever, to have one authentication to cover all our services. We had fingerprinting, A/B testing, traceability IDs, local, context enrichment, bot mitigation, you name it, we have it. So we decided to build our own function runner and a framework. We also called it Edge function, sorry, AWS. We wrote it with TypeScript, and it executes multiple modules or submodules asynchronously all together. We have a system to interrupt any slow executions, so to protect every request. We have a permission system. We control which module is allowed to interrupt the request, send a status code, which module is allowed to send an external API calls or not. You know, Lambda on the edge, it's quite critical. We're covering all our system. So we also decided to build a global configuration object where we can easily turn on and off any of the submodules, or if we see anything wrong, we should be able within 10 seconds to propagate a configuration that will be there everywhere. And finally, we kept our SLO, or objective of latency, under 10 milliseconds, executing those multiple submodules. And this is how our module look like. Our framework have to be imported into the individual submodule. They need to implement our interface and implement their own handle function. And then we have a packaging pipeline that takes our function runner and all the submodules, packaging them into one Lambda. And then we simply attach that Lambda into our multiple CloudFront distributions. To get to that point of having that global object where we can propagate and control what's happening on the edge, in the beginning, we used DynamoDB global tables. It worked really well for us for a while. But then we did an experiment. We found out if we just put all our configuration in a JSON file, put it also in CloudFront with some caching headers, that actually was faster and more cost-effective for us. And this is how we ended up running our Lambda on the edge framework. Finally, actually not all workloads fits within CloudFront. We did have a few use cases where we expanded the definition of what we called our edge into something beyond the CloudFront. One example of that, we have something in Booking called Booking affiliates. Those are basically thousands of domains and subdomains that are simply CNAMEd into our load balancers. We actually don't control the DNS zones of most of them. They're simply an external vendor that we have an agreement with to redirect the traffic to our services, and we have an agreement around it. So for some of those, we don't even have an SSL certificate for. And we needed to also achieve the same global low latency. And we needed something that is resilient. In Booking, we have a rule that everything has to be deployed in multiple regions to make sure our resilience have enough nines to make us sleep at night. And finally, it needed to be protected by WAF and Shield and adhere to the same security standards. So the solution was actually quite simple. We just use application load balancer with a catch-all redirect rule. And then we protect that point with WAF and Shield. And then we used the AWS Global Accelerator. It's basically an Anycast service. Once you attach it to your application load balancer, now you have a static IP. It is being broadcasted or announced in all the edge location. And it simply sends back the redirect to all your customers. So in summary, we told you today about our journey, how we started with our own hardware appliances into building our own distributed load balancer into using CloudFront as our edge. We told you about how we build our foundation of security and observability, and how we are data-driven, and how we built an experiment around using CloudFront. And then we told you how we use Route 53 behind the CloudFront to allow us to shift the traffic and try to balance it between the different origins. And then we talked about what, for me, is the star of the talk of tonight, is the persistent connections between CloudFront and the origins, and how that actually achieved much lower latencies for our reverse proxy and dynamic traffic. And we gave you some notes how you should be aware and make sure to educate yourself of the CloudFront standards and limitations. And as much as you think you made your homework, you still need to send that 1% canary so you can see actually what happens and learn from that. And finally, we told you about edge compute and how we use Lambda on the edge to really modernize our infrastructure.
Awesome, thank you, Ali. So, in addition to some of those talking points that Ali just shared, I want to leave you all with some key takeaways. If you could take anything away from this presentation, I'd like to think I summarized them here. First and foremost, CloudFront can be used as a reverse proxy. It's great for dynamic content acceleration. You don't even have to configure caching. However, if you did, it would also help way more. A lot of times when customers use API delivery services, they don't think about caching. In reality, we find that even if you cache it for a very short amount of time, there's a lot of value to that, right? The second point is improve your performance, availability, and security posture. It's very easy to deploy a reverse proxy in front of your HTTP public-facing endpoint. Let us take care of a lot of the heavy lifting when it comes to figuring out DDoS protection, perimeter protection, and so forth, right? Let those capabilities be used towards your advantage, and it's actually an architectural best practice to use CloudFront for any public-facing endpoint. Next, it's important if you're migrating and you're going through a lift and shift, you need to build experience, right? And sometimes there are things that you overlook when you just go with lift and shift that you might be able to plan for accordingly if you experiment and start using cloud native services a little earlier. So CloudFront's a good example of this. You saw all the integrations that we have. You saw some of the operational tools through CloudWatch monitoring, logging, and so forth. All of this is super valuable if you're new or at some point adopting the cloud. Last, test, measure, assess. You will have to adapt. Ali pointed out that even when they planned, we worked very closely with them. Even when we planned, we looked at all the requirements. We did the foundational testing. We did a POC. There's still stuff that you're not going to uncover in that initial planning and execution phase. So roll out slowly, test it, measure it. Make sure you get at least 90–95% of the way there. And then just be aware that there's going to be little things that you have to tune for as you kind of go full production. And lastly, this is a point that I kind of want to highlight is, migration is one topic, using a cloud service is another topic. But when you use CloudFront, it actually makes it easier for modernization. If you think about some of the routing capabilities that we talked about today, it could help you strangle a web application. It could help you shift traffic slower in different ways, in more advanced ways beyond just DNS routing. And lastly, I'd like to leave you with some resources. So this is our developer portal page, this QR code that I have available for you. This is where my solutions architecture team publishes a lot of our content. We see customers draw to this a lot because we're really trying to highlight use cases that are common across a lot of customers that we stand by. So if you have time, please visit this website. And with that said, take the picture. With that said, we'd like to thank you all. Please remember to submit your survey. We'd love to hear it if you like this type of content, so it'll help us as we plan future events.
Yeah, thank you, everyone, and please keep the conversation going. You can reach to us in LinkedIn, or we will be in the corridor after this talk. If you have something similar, reach out to me. I would love to network and learn from you, and we are happy to share whatever we do. And yeah, thank you, and thank you, Tino.
Awesome.